So taking a look at this circle, we can definitely write the equation of this circle in implicit form, just like we did last year. And as a review, circle properties that would be useful to know to write the equation would be the radius and the center. So if we try to find the center, I'd say that point looks pretty good. And then the radius to the edge would be 1, 2, 3, 4, 5 units. So when we write the equation of a circle, we're going to have an x variable squared plus a y variable squared, and that's going to equal our radius squared. So if we square 5, we'll get 25. Now a simple circle will just be x and y, and that's if it's centered at the origin. But notice how this one is centered elsewhere. So instead of being at the origin, the center was moved right 3 and down 2. So we're going to show the idea of moving right 3 by subtracting 3 from the x, and we'll show that it moved down 2 by adding 2 to the y. Now that we have the implicit equation of the circle, we can find the derivative of this. Pretty simple. We're just remembering to write a dy over dx anytime you take the derivative of a y variable. So looking at this first group here, we're going to have to go ahead and use our chain rule process with that because we have an inside and outside section. So we'll bring down the 2, we'll keep the inside, new power will be 1, we'll multiply by the derivative of the inside, which would be 1 as well. So we'll finish off the chain rule by multiplying by the derivative of the inside, which would be 1. Let's go ahead and add the next derivative of our next section or next term here, and we're going to have to use the chain rule again. So we'll bring down the 2, we'll keep the inside, new power would be 1, and now we have to take the derivative of the inside. So the derivative of y would be 1, just like the derivative of x would be 1, but since you're taking the derivative of a y variable, we need to write dy over dx. So the derivative of y is 1, and since we took the derivative of y, we'll write dy over dx. We'll add the derivative of 2, but that's 0, so that's negligible. We then have to take the derivative of the right-hand side. So just like in algebra, what you do to the left, you got to do to the right. And I'd be willing to bet my bottom dollar that whenever we go through this section, there will be some people that simply just copy down 25, okay, just out of habit. But the thing is, we're taking a derivative. So we do not write 25 here because the derivative of 25 would be 0. Okay, so be careful with that. Don't just copy down the number. Remember that you have to take the derivative of it. So if this is a derivative, we're going to go ahead and solve for that derivative symbol, dy over dx. That way we have just some equation we can use to help us find the equation of a tangent line. Now, some things you can do with this, we can probably clean this up a little bit. For instance, we don't have to write the 1 there, and we don't have to write the power of 1, so we can write this as 2 times x minus 3. And kind of the same deal here, we can write 2 times x plus 2. We don't have to write that power of 1. We don't have to write that coefficient of 1. So we'll just have the dy over dx written afterwards. So if we're trying to solve for this variable or this term, we'll go ahead and subtract this quantity to the other side. And to get dy over dx all by itself, we can divide by 2 times y plus 5, or sorry, y plus 2. So when we divide this quantity over, the 2's would cancel, but we'll still have the negative in front, and on the bottom we'll just have y plus 2. So there's our derivative for any point on this circle. And notice how in order for you to figure out the slope at any point on this circle, you would need the x-coordinate as well as the y-coordinate for the circle. So this is what's a little bit different than the previous derivatives we've been finding. Typically we've just been plugging in x's to figure out the slope of the tangent line, but now we might have to know a y-coordinate to help us with that. And that's what we're going to practice with the table at the bottom. So let's say we wanted to find the slope at this particular point on the circle. So 0, 2, we're going to try to figure out what's the slope of the circle at that spot. So x value, y value, we can go ahead and plug those into our derivative, because after all, derivative means slope. And looks like we'll get 3 over 4. So at this point, you should be able to go up 3 over 4, and you could go the other way, down 3 over 4, and you'll have the tangent line at that spot. All right, so everything seems to be making sense. Let's go ahead and try to find the other values for these other points. So 3, 3 would be right here. And notice how we would have a horizontal tangent line at that spot, aka a derivative of 0. So let's see if that is actually what happens when we plug this into our derivative equation. Looks like we'll get 0 over 5, which is 0. And that is signifying a horizontal tangent since the slope is 0. All right, let's go ahead and try the next one. So 8, negative 2, looks like we're at this rightmost point. And if you were to draw a tangent line, notice how it would be vertical. So in terms of our equation here, a vertical tangent line means an undefined slope. And since our derivative is a fraction, the only way a fraction is undefined is if the bottom is 0. So let's see if that happens when we plug in this point. Looks like we'll get negative 5 over 0, which is undefined. And based off of this graph, we have the vertical tangent. Now, just because the derivative is undefined doesn't mean you always have that vertical tangent. If a derivative doesn't exist, other possibilities are those sharp points or maybe an endpoint. So it's just this particular example where we have that vertical tangent happening. All right, go ahead and try the rest of them just for time purposes, trying to make this fairly quick for you guys. I'm sure that you can do the rest. I'll go ahead and write down the derivative solutions for the rest of the table, but please make sure you can go ahead and get those based off of the derivative that we found using the implicit differentiation method. Okay, every time we find the derivative of a y, we have to write dy over dx.